And local blood flow is how much blood gets to an area, okay? So it depends on degree of vascularization. So how many vessels you have in that area. The more vessels you have, the more blood flow you're going to have there. The other thing that affects the local blood flow is myogenic response. So as the blood flow increases in an area, the vessels are able to adjust the blood flow by constricting and limiting flow of blood to that area, and vice versa. There are also some local regulatory factors, and total blood flow also affects local blood flow. I want to go back to the degree of vascularization. So when we talk about degree of vascularization, we should be familiar with two terms, and these are angiogenesis and regression. Angiogenesis, angio has to do with vessels. Genesis has to do with formation. So angiogenesis means formation of new blood vessels. And this is associated with growth of new vessels. And we see a lot of angiogenesis going on in embryonic and fetal development. The rate of angiogenesis is really high there. As well during during childhood, you have a really high rate of angiogenesis. We can see angiogenesis in adults as well. So if we think about someone that begins to work out, for example, okay, if someone begins to work out, they start to build muscle ultimately, hopefully that's goal, right? And so as the new muscle is being built, the muscle needs new vessels, right? And so you're going to see angiogenesis or formation of new blood vessels so that these new blood vessels can supply the new tissue. We're also for regression. Regression is degradation of vessels when you're losing some tissue. So we can use that same person that's working out, right? They're building muscle, but they're going to lose adipose tissue. And so as they are losing the adipose tissue, they no longer need the blood vessels that used to supply that adipose tissue, and so you're going to see regression there. Some local regulatory factors. This is going to have to do with vasoactive chemicals, so some vasodilators, vasoconstrictors. There, depending on what the tissue is doing, chemicals act as vasodilators. Some act as vasoconstrictors. There's a special type of autoregulation that's called reactive hyperemia. This is when tissue is temporarily deprived of nutrients and oxygen, but those cells are not dead. They're not dying. They're still working. They're just deprived of these nutrients and oxygen, and they're producing wastes. Since the blood flow is temporarily paused, these wastes are not being taken away from the area. And so when you restore the blood flow to that area, there is a really quick rush of blood to that area because of the high levels of the wastes that are related there. And so that's referred to as reactive hyperemia. The classic example of reactive hyperemia is when you enter a warm room from cold outside. What's going to happen there is your cheeks get red really quickly when you come from cold into a warm room. And that's because while you were out in the cold, we temporarily paused blood flow to the capillaries that are under your skin of your face, so that you're not losing heat. So those cells were producing waste that are not being taken away because the blood flow is limited to that area. And so when you enter the warm room, there's no longer need for you to conserve heat, and so blood rushes into your face really quickly, and your cheeks get red for a little while, and that's reactive hyperemia. The main kind of a signal for the blood flow to increase to an area is accumulation of waste. So this could be the carbon dioxide or lactic acid. So it's not really the fact that the tissue is deprived of nutrients and oxygen. It's the fact that wastes are accumulating in that area and they're not being taken out. So what generally would happen just in a normal case of increasing metabolic activity is that you would see like regular blood flow going to an area. So imagine a muscle, right? A muscle at rest has some blood flow to it, okay, but it's not super high, just regular to keep that muscle healthy and thriving. But if that muscle begins working, if the metabolic activity of that muscle increases, the blood flow is still normal until these vasoactive chemicals accumulate. So this would be carbon dioxide, perhaps lactic acid, because that's a byproduct of anaerobic respiration in the muscle. And so as these start to build up, because the regular blood flow is not able to take them away fast enough, these wastes are going to cause vasodilation. Vasodilation means that we open up the vessels that are in that area, and that allows more blood to come to the area and remove the buildup waste, as well as bring in extra oxygen and nutrients to support that increased metabolic activity. Some other or another example of these local regulatory factors is when our tissue responds to damage, or if we're trying to, it's part of a defense mechanism. So we'll be talking about inflammation in chapter 22, and this inflammation is going to be associated with quite significant vascular changes. It's going to involve vasodilation. We also, like if your tissue gets damaged, there are chemicals that are released during that damage. Nitric oxide, big one. This is a vasodilator, and it can increase blood flow to the area so that repair of the damaged tissue speeds up. Okay. And then the last thing that affects local blood flow, or what the local blood flow depends on, is total blood flow. Ultimately, total blood flow affects your local blood flow too. So the more blood you have circulating through your body actively, the higher the local blood flow for most parts of your body are going to be. So those depend on each other. So that's our local blood flow. Now, let me see where we got blood pressure. Okay, so this is going to take us to the blood pressure, resistance, and total blood flow also. Okay, so as I mentioned in this picture right here, blood pressure really is defined by the amount of blood that you have in the vessel. So it is really, in scientific terms, blood pressure is force per unit area that we exert on the wall of a blood vessel. It is expressed in millimeters of mercury, so this is the right there. And we can talk about different types of blood pressure. So here we're looking at capillary blood pressure, okay, which is about 40 or maybe 35 millimeters of mercury. I forgot to add something to this, and that is that blood pressure in the venule after blood passes through the capillary is about 20. Okay, millimeters of mercury. So those are kind of important numbers. So this suggests, I mentioned that close to the heart, the blood pressure is pulsatile. It's given in two values, so about 120/80 is that ideal set of numbers that you want to see. But by the time we get to the capillary level, it's much lower, and it's just one number because it is now smoothly flowing, continuous flow. It is not pulsatile anymore. And then when we exit the capillary, we are even lower than that. So what you can see here is a trend. The blood pressure decreases as we're going away from the heart. And this is what blood pressure gradient is. Okay, this is what allows the blood to actually flow through your body. It allows us to send the blood this way. Okay, if this 20 millimeters of mercury wasn't 20, if this was higher blood pressure than here, then the blood flow wouldn't happen in this direction. Okay, blood flow has to flow to the area of lower pressure. Okay, so that's the blood pressure gradient. Blood pressure gets lower and lower as we're going through our cardiovascular system. By the time blood flows to the heart, by the time it returns back to the heart through the vena cava, it is close to zero. Okay, and So blood pressure gradient is our driving force that allows our blood to circulate through our body. I've mentioned we have several different types of blood pressure that we can describe. So arterial blood pressure is pulsatile. This is the blood pressure in the arteries. And when we measure arterial blood pressure, we measure it in relationship to or in reference to the larger vessels that are close to the heart. So normally when the doctor and they take your blood pressure, they use your arm. This is where we're looking at brachial artery at this point. The arterial blood pressure is the highest when the heart contracts, okay, when the ventricles contract, because this is when they're actually pushing blood into the heart. And it is the lowest when the ventricles relax, because now they're not actively pushing the blood into the arteries. So the ventricles contract. This is called systolic blood pressure. And then when the ventricles relax, this is called diastolic blood pressure. And I've mentioned that we are, striving to have those numbers be 120/80. Systolic blood pressure is always going to be higher. Okay. Systolic blood pressure is the pressure during the heart's contraction, so it cannot be lower than when the heart is relaxed. Okay. So systolic pressure is always the higher one because it's during systole, and diastolic is during diastole. So that's our arterial blood pressure. We can look at the difference between these two, between systolic and diastolic blood pressure. And the difference between the two tells us the pulse pressure. And pulse pressure is important for us to pay attention to because it tells us how elastic our arteries are. So when the vessels are experiencing diastolic blood pressure, okay, blood is not actively being shoved into the vessels, right? But then when the heart contracts, it stretches the vessels, and that's going to be your systolic blood pressure. So if your vessels are nice and elastic, they're able to kind of absorb some of that pressure as the blood is entering the vessel during systole. Okay, if your blood vessels are not elastic, if they are rigid or hardened and just not healthy, they're not able to stretch, and therefore the pulse pressure would be higher. Okay, the diseased artery would not be able to absorb some of that pressure. So the higher the pulse pressure, the worse your arteries are. Okay. So ideally, if our ideal blood pressure is 120/80 for arterial blood pressure, then I guess ideal pulse pressure would be 40. Okay. And the higher it is, the more diseased your arteries are. Another important blood pressure that we need to talk about is the mean arterial pressure, and this is also known as the MAP. And this one, mean means average, right? And so this is telling us what is the average pressure in our arteries. Taking into account the systolic is different than diastolic. When we look at the mean arterial pressure, even though mean is our average, we cannot do like a regular average, okay? And that's because at rest, we know that the cardiac cycle is in systole 1/3 of the time, and in diastole 2/3 of the time. Okay, so the heart is in systole 1/3 of the cardiac cycle, and in diastole 2/3 of the cardiac cycle. So the rest of the heart lasts longer than the contraction, which is important because this allows your heart to rest and not get fatigued. So the way that we calculate this is, let me take this away, is through. Okay, we can say that, let me move a little bit. We can say that mean arterial pressure is equal to, I'm going to make a big line, and we said that diastole lasts 2/3 of the cardiac cycle, so we can say 2 times diastolic plus 1 times the systolic pressure Okay. And since we're talking about, 2/3 and 1/3, total number of parts 3, so we're going to divide this by 3. And so here you can see that systole is 1/3 and diastole is the 2/3. Okay. There is a different equation in your textbook, and that one, I don't think it really clearly shows where the number is coming from. If you use the other equation in your textbook, which is like something with pulse pressure and some, like a diastolic pressure or something like that, you will get the same result as if you're using this equation. This is a standard way to calculate weightage. Okay, so where we take into account the weights of the parts. All right. So this is the equation for the mean arterial pressure. Mean arterial pressure tells us how well your body is perfused. It shows whether your body has adequate perfusion. If mean arterial pressure, if the average pressure in your arteries is too low, that means that that the capillary exchange, so going back to this, okay, it means that if overall your blood pressure is too low, it means that this is going to be lower too. It means that the hydrostatic pressure here is going to be lower, and that means that the filtration might be happening at a lower rate, or it might be lower than the colloidosmotic pressure and not happening at all, which would mean that you are probably not going to survive that. Okay. So the overall blood pressure is going to always be reflected down to the capillary level. Okay. So if your mean arterial pressure is too low, this number will be too low and filtration will happen less. Okay. Which means that the cells over here are going to be deprived of nutrients and oxygen, and also wastes are not being removed efficiently enough. If your mean arterial pressure is too high, that means that this number right here is going to be higher, which means that the hydrostatic pressure here is going to be higher. Filtration is going to be happening at a higher rate, and you might experience edema because of this. So remember how we were talking about heart and how if one ventricle cannot keep up with the other, how it can create a backup or increase in pressure. It would increase pressure here, and that's that's one of the reasons why we could see this. But it would ultimately increase pressure at the capillary level, and it cause excess fluid being filtered out here. Okay, so you would experience extra fluid here, which causes swelling. Okay, the higher mean arterial pressure, the biggest risk of high mean arterial pressure for a longer period of time is development of cerebral edema, and cerebral edema is where edema happens in your brain. So this is where the capillary exchange happens. Excuse me, happens at a higher rate in your brain capillaries. In our brain, we don't have lymphatic vessels like we have in other tissues, and so normally lymphatic capillaries, they could make up for some temporary increase in filtration and remove some excess fluid from there. But in the brain, we don't really have that going on as much as what we see in other tissues. And so cerebral edema is a high risk of chronic mean arterial pressure. Capillary blood pressure we've already talked about. So capillary blood pressure is about 40 here, and then about 20 as it enters the venule. So it gets lower and lower. And then the last type of blood pressure that we'll talk about is the venous blood pressure. And venous blood pressure, so I've said that as the blood enters venule, it enters at 20 millimeters of mercury. As these venules merge into larger and larger vessels, veins have larger lumen. And so the blood that's filling the veins, it's not going to exert as much hydrostatic pressure as what it would do in the arteries, because arteries have a smaller lumen, so you need less fluid for a certain pressure to be happening. So veins are going to have a larger lumen, therefore the pressure is going to be lower and lower. And as I've mentioned, by the time we get to the vessels that are before the heart, the vena cava, the blood pressure in those vessels is close to 0. So this is not enough force to move the blood through the venules or veins. Even 20 millimeters of mercury would be too low to push it, towards the larger vessels. And so veins actually don't, because they don't feel the pulsation of the heart anymore. Veins rely on a couple of other mechanisms that move blood through our system, and those are skeletal muscle pump. Okay, let me share this with you. And then the respiratory pump. Okay, so in skeletal muscle pump, what this means is skeletal muscle that surrounds veins. Whenever the skeletal muscle contracts, it will squeeze the vein, and it will squeeze the blood that's inside of the vein. Now, remember, if you watch the first part of the vessels, we talked about veins having valves in them. Those valves are important so that the blood moves only in one direction. Those valves work the same way as the valves that we see in the heart, the semilunar valves. So when the skeletal muscle contracts right here, okay, it pushes the blood this way, which opens the valve in this direction. But if the blood goes in here, it gets trapped in those by that valve. It's not allowing blood to go down. Okay, it only allows blood flow in one direction. Okay. And then the respiratory pump. Respiratory pump is kind of the same mechanism, but we're not using muscles. We are using the changes in pressure in our thoracic cavity versus our abdominal cavity. So whenever you are inhaling, your diaphragm contracts and it gets flattened like this. Okay, so you can see the diaphragm right here, and it's flat. Okay, what that does is it squeezes or compresses everything in your abdominal cavity, including the veins. Okay, so it's kind of the same mechanism as with the skeletal muscle pump, but it's not the skeletal muscle really that's doing that. It's the pressure, general increase in pressure in the whole abdominal cavity. Okay, when you exhale, your diaphragm goes into relaxed position, which relaxed position of the diaphragm is actually like this. So it's like a dome-like shape. And when that happens, it compresses everything in your thoracic cavity while relaxing your abdominal cavity. Okay, and so the movement of blood in our veins in our thoracic and abdominal cavity depends on the respiratory pump. Okay, and then everywhere else it would be skeletal muscle pump. You can see the blood kind of pool in your hands. If you stand upright and you just let your hands rest next to your sides shortly, you should be able to see that the veins on the back of your hand are starting to fill with blood, and they kind of look like they're popping out. And that's because you're still and your muscles are not compressing on those veins. Okay, but as soon as you start moving that hand, it moves the blood through your vessels, and the veins go back to normal. Okay, so you can kind of observe that. Actually, if you're looking at the back of your hand and you see that the blood pools here and there, you might see like a bump in that vessel, and this is where the valve would be. Okay, so the vessel kind of dilates a little bit before the valve, so you can actually see your valves in your hand. All right, let's talk about resistance, because so blood flow is a relationship of, or kind of a product of, the total blood flow and the resistance. Resistance is what opposes the flow. And resistance, I don't have that picture here. Again, there's not a whole lot of pictures for this part. But okay, before I get to resistance, if you look at clinical view on page 806, you can see varicose veins and what's kind of happening there to that person. Varicose veins are caused by excess fluid in the veins that is not being moved regularly through your body. So that person has pretty significant varicose veins on the on the right leg. And this is so if that blood kind of sits in the veins sometimes collapse and kind of become visible like that. And this is only fixable by surgery, so they can fix that by operating on it. But anyway, so those are varicose veins. The one thing about veins, the other thing about veins is that veins serve as blood reservoirs. I mentioned that veins have a larger lumen, so they actually hold most of your total blood in your body. Okay, so veins serve as blood reservoirs. They have up to 55% of blood in your body at rest. Okay, so know that veins are blood reservoirs. And yeah, so that's that. So let's talk about that resistance. The resistance is the opposition to flow. It depends on three things: how viscous your blood is, the diameter of the vessel, as well as how long your vessel is. Okay, so that's like talking about a specific vessel. The higher the viscosity is thickness of your blood. So the thicker it is, the slower or the higher the resistance will be. So think about this. There's a good, like an integrate or learning strategy thing on page 808. If you look at page 808, there's that learning strategy there that compares the flow of blood to like different things that people drink through a straw, where straw would be your blood vessel and whatever you're drinking would be the blood. So for viscosity, they're comparing you drinking water through a straw, which is very viscous, right? It's water, compared to a milkshake. Okay, milkshakes are thick. So which one would be easier to drink? The water. Okay, the thicker the substance is, the harder it is to move it through that straw. Okay, so the higher the viscosity, the higher the resistance. The vessel length is also affecting our resistance. So the higher the vessel length, the higher the resistance. This is like, imagine that you're drinking something through a regular straw compared to like one of those that kids seem to love, those twisty straws with various shapes. Okay, which one do you have to work for harder? Okay, it's harder to drink from that twisty one than just a regular, shorter, regular straight one. Okay, so the higher the vessel length, the higher the resistance. And then for the diameter, or this has to do with the size of the lumen, right? So for the diameter, the smaller the diameter, the higher the resistance. So that last one, the diameter, is inversely proportional. Okay, the smaller the diameter, the higher the resistance. The other ones were directly proportional. So higher viscosity, higher resistance. Higher vessel length, higher resistance. But for the diameter, it's smaller the diameter, the higher the resistance. And when you think about the diameter, think about, is it easier to drink through like a really thin, skinny straw, like those coffee stirrers, or those, little tiny straws that are just used to stir things? Or is it easier to drink from like a regular straw that you get like at McDonald's? Okay. And it would be easier from the regular straw with the larger diameter than using a coffee stirrer to drink something from it. So that's our resistance. So let's talk about how we regulate blood pressure now. And we're going to talk about the regulation of blood pressure. This is going to be short-term regulation, okay? So these things are going to help with short-term regulation. Let me see where I think I included a picture right here. So we're going to talk about the cardiac or cardiovascular center. There's a cardiovascular center in your within your medulla oblongata. So that's right here. And the cardiovascular center has two subcenters. So it's made of two subcenters, and those are vasomotor center right here. And then you have the cardiac center underneath that. And if you've watched the section on the heart that's on YouTube, then you should know, or maybe kind of remember that you heard it already, that the cardiovascular center is associated with the sympathetic innervation, and cardiorespiratory center is going to increase your heart rate. It's going to increase force of contraction. And then cardioinhibitory center is going to decrease your heart rate, and that's associated with parasympathetic innervation. Okay, but cardioinhibitory center does not have an effect on force of contraction, just the heart rate, and it decreases it. So that's cardiac center. The vasomotor center. So cardiac center is innervated by both sympathetic and parasympathetic innervation, but vasomotor center is only innervated by sympathetic division. And the response of vessels, like whether they're going to vasoconstrict or vasodilate, depends on the receptors that are present in tunica media of the vessels. Okay, so there are different types of receptors for different either neurotransmitters or hormones in vessels, but the two most common types of receptors are alpha-1 and beta-2 receptors. The alpha-1 receptors are interacting with norepinephrine, and they contract in response to norepinephrine binding to the alpha-1 receptors. The the beta-2 receptors, these interact with epinephrine, and the binding of epinephrine to beta-2 receptors causes vasodilation. Your vessels, most of vessels have the alpha-1 receptor, okay, and fewer vessels have the beta-2. Now, norepinephrine and epinephrine, they both come from the same gland. They both come from the medulla of the adrenal gland. So if the adrenal gland is stimulated to release these chemicals, they will be released both at the same time. Overall response of activation of vasomotor center is going to be increased peripheral resistance. You're going to increase resistance because most of your vessels have that alpha-1 receptor, and so there's going to be more alpha-1 receptors stimulated to contract than the beta-2 receptors that are stimulating vasodilation. So overall effect is going to be increased peripheral resistance because we're causing vasoconstriction. The vasoconstriction is going to, with it, bring a larger circulating blood volume. Okay, think about this. Your veins are your blood reservoirs, so most of your blood is in your veins. If we cause vasoconstriction of those veins, that's going to move blood into active circulation. So now you're going to have larger circulating volume. And this also means that there will be a redistribution of blood flow. We're moving it from those blood reservoirs into active circulation and supplying more places that are metabolically active whenever they're needed, okay? So that's our vasomotor center. There are also baroreceptors in your body, and baroreceptors are receptors that respond to stretch of vessels. So so under normal circumstances right now, as you're at rest, there's a certain blood flow that's happening through your vessels, and these baroreceptors, there are two places where we find these baroreceptors: aortic arch and carotid sinuses is where we have these baroreceptors. So they are firing at a certain rate right now. But if your blood pressure increased, then these baroreceptors are going to increase their rate of firing. And that tells your brain, okay, something happened, our blood pressure went up. And that will cause ultimately vasodilation. Opposite is true if your blood pressure falls, if it decreases. Now those baroreceptors are not firing as quickly, and that tells your brain, okay, our pressure is too low, we have to increase it. And so vasomotor center will be activated to increase that peripheral resistance, cause vasoconstriction, redistribute blood flow to maintain the regular blood pressure. The baroreceptors also will stimulate the cardiac center, cardioexcitatory, or cardioinhibitory based on how the pressure is changing. So it's going to the baroreceptors will have an effect on both the vasomotor center and cardiac center. And then we also have chemoreceptors, and chemoreceptors We haven't talked about respiratory system really, but it's kind of a secondary mechanism of regulating blood pressure. It's mostly it has to do with pH of your blood. So chemoreceptors, we have them in aortic bodies and carotid body. And this is why we see baroreceptors and chemoreceptors in these two places, is because it gives us two places to check the blood pressure before the blood enters the brain. Okay, so for the rest of the body, just that one, the aortic arch is fine, but we have that second checkpoint in the carotid sinuses, okay, so that the pressure in the brain is maintained at what it needs to be. Okay. The chemoreceptors react to increased carbon dioxide, low pH, which these two have to do with each other. If you increase carbon dioxide, your blood or your pH gets more acidic, and that's because carbon dioxide and water in blood react with each other and create an acid. Also, low oxygen level can stimulate these chemoreceptors. And so if you increase carbon dioxide or decrease pH or decrease oxygen, this stimulates increase in firing of these chemoreceptors, and that's going to stimulate vasomotor center, which will cause vasoconstriction, redistribution of blood flow. Blood will go to the lungs where we can get rid of this excess carbon dioxide. Okay. But again, the chemoreceptors are more like a secondary mechanism of blood pressure regulation. It's it has to do more with the pH and eliminating extra respiratory gas, the carbon dioxide. So that's chemoreceptor centers. And then there's also a higher brain center that can influence blood pressure. Like if we think about fight or flight, your blood pressure is going to change if your body is in fight or flight response. Anxiety also. And then the limbic system can alter blood pressure as a response to certain emotions or memories. So those also can affect your blood pressure. There is also the last thing for regulation of blood pressure is hormonal regulation. And that's not on this picture, but I do have one that talks about hormones. And this will come back to us when we talk about urinary system, because the hormonal regulation of blood pressure really has to do with regulation of the amount of water that you have in your plasma. And that is directly going to affect blood pressure, because the more blood you have, the higher the volume, the higher the blood pressure is. So there are three hormones that are going to increase blood pressure. Okay, they are responding due to lower blood pressure, and they are renin-angiotensin system. That's our first one, and then aldosterone and antidiuretic hormone. Okay, so these three again are going to respond to low blood pressure. Let me see if I can write it here somewhere. Okay, so hormonal regulation. I have to click this every time. Okay, so we have response to low BP. These would be your renin, angiotensin, I think I spelled it right, system. That's our first one. The renin-angiotensin system is the most complicated, so but it's really not that complicated. It's just the description of it is the longest. Renin is a substance that's released out of your kidneys as a response to low blood pressure, or if sympathetic nervous system initiates this, but most commonly it's due to the low blood pressure. So renin is released by your kidneys to the blood. The angiotensin, the second part of this system, angiotensinogen actually, is released by your liver continuously. It doesn't really require a stimulus for release, it's just released, okay? And it is part of your blood. It's one of those plasma proteins that you have. Angiotensinogen is inactive, so without renin, it doesn't do anything, it's just there. But if angiotensinogen meets in, they interact with each other, and renin converts angiotensinogen into angiotensin 1. Okay, then this angiotensin 1 is still inactive, and it has to be activated. And what activates it is angiotensin converting enzyme, and this is an enzyme that converts angiotensin 1 into angiotensin 2. Finally, our angiotensin 2 is the active hormone that will cause vasoconstriction. It will stimulate your thirst center, and it will also regulate your urine formation. It also stimulates the release of aldosterone and ADH, which are the other two that respond to low blood pressure. The angiotensin converting enzyme, something that's kind of interesting about it is that majority of this enzyme is found in our lungs, and that's because your active, the blood that's in your active circulation has to pass through the lungs to get oxygenated. So it's the most efficient way to convert angiotensin 1 to angiotensin 2. So that is our renin-angiotensin system. I said that one is the most complicated, but hopefully you didn't think it was that complicated. The second one before I get into the second one, I said that the effect of it is that it stimulates thirst center. This would make sense because if you add water, digestive system, that water will be absorbed into your blood, and so the blood volume would increase. Okay, and then urine formation control, when I said that, is what that means is it's going to limit the amount of water that you lose in your urine. Okay, so that's those are the effects of angiotensin. Okay, the other two are aldosterone and ADH. Aldosterone and ADH can be released by the presence of angiotensin 2, but they also respond to low blood pressure. So this is, I'm going to write aldosterone. Okay. Aldosterone comes from the adrenal cortex, and it increases sodium absorption. Okay. Now, what does sodium absorption have to do with blood pressure? Well, sodium absorption actually increases water reabsorption as well. So the more sodium that you have in your blood, the more water you're going to also retain. So where sodium goes, water goes with it. Okay, and that's why people that have chronically high blood pressure are usually put on limited sodium intake diet. Okay, so that they're not retaining water. So that's aldosterone, and then the last one is ADH, or antidiuretic hormone. Antidiuretic hormone comes from the posterior pituitary. It's released by posterior pituitary. It is made by hypothalamus, right? It's one of those two that hypothalamus sends to the posterior pituitary. The ADH is also going to be responding to low blood pressure. It's also going to respond to high blood concentration. If your blood is too concentrated, it means you don't have enough water in there for all those solutes, and so that's what ADH does. Antidiuretic hormone prevents diuresis, so it's against diuresis. It's against water loss. So antidiuretic hormone acts on your kidneys, and it will cause increase reabsorption of water in your collecting tubules, so you're not forming a lot of urine, and you're conserving water. Okay. If you have extremely low blood pressure, the ADH can also cause blood vessel constriction, but this is like extremely low blood pressure and like extremely high ADH levels that causes. It's not a normal function of the ADH. Okay, so those are the three that respond to low blood pressure. Then we have one that responds to high blood pressure. So the response to high blood pressure, this hormone is known as atrial natriuretic peptide, or ANP for short. And atrial natriuretic peptide, when you look at the first word, atrial, that should give you a hint where it comes from. It comes from the right atrium of your heart. So this hormone comes from the heart. It is going to respond to high blood pressure. So that one is the only one that responds to high blood pressure. The other three respond to low blood pressure. And ANP is going to cause vasodilation, so that your vessels open up and are not, release some of that pressure, relieve that tension there. And then AMP is also going to increase urine output. So AMP is going to make you pee more, okay? And that's because you want to get rid of the excess water so that your blood volume goes back to normal, okay? And that's the hormonal regulation. Let me see. So that takes us, I don't know where we are in the textbook. That brings us to page 816. This talks about blood flow during distribution during exercise. Basically, the blood flow to different tissues during exercise changes to meet the demand of those tissues that are going through increased metabolic activity. That's kind of what that says in a nutshell there. And then after that, it goes into pulmonary circulation and then systemic circulation. The rest of the chapter is identification of vessels. So that is where you would go into, let me see if anybody actually started this already. But I created that activity there, the vessels drill. Use that, use your unlabeled pictures for chapter 20 that I uploaded for you, and practice labeling. That is the only way that you will get the names of the vessels, right? And let me see, anybody started that yet? And it's called vessels drill. Nope, nobody started that yet. Okay, you start early on that. And that's that. For pulmonary circulation, I do want to point out that that I guess we don't need to see this anymore. But for the pulmonary circulation, I want to point out that the blue vessels are your arteries, the red vessels are the veins. So remember, in pulmonary circulation, the colors are flipped compared to your systemic circulation. And we kind of already described pulmonary circulation when we talked about the heart. So, you should be able to tell me that the right ventricle pumps the blood into pulmonary trunk splits into pulmonary arteries flow, enter the lungs and branch, and blood flows through the lungs where it gets oxygenated, and then oxygenated blood gets collected by the venules, and then it returns to the left side of the heart, the left atrium. So that's pulmonary circulation. Just don't forget that the colors are switched with pulmonary circulation, okay?